contained in Rn plus k, and this is an n-dimensional varifold, stationary in U, and we're assuming theta 0 is in the support. As usual, we're going to let mu be the Hn restricted to theta. And 0 is in the support of mu. And we take a ball B rho, standard at the origin, contained in U. And one of the important hypotheses is that theta is bigger than or equal to 1. Mu almost everywhere. And then the key hypothesis is that the amount of measure in the ball, in a small ball centered at the origin, omega n rho to the n, is just a bit bigger than 1. And we're going to assume delta is small. So delta bigger than 0 and to be assumed small. But for the moment, it's just an arbitrary positive constant. And I pointed out that a couple of things. First of all, remember that these hypotheses imply that we played around with the monotonicity formula. Oh, okay. No, it's good. We played around with the monotonicity formula, and we showed that these hypotheses, call them star, we showed that star implies these sort of uniform estimates on the densities. So we said that mu sigma b sigma xi over omega n sigma to the n is always bigger than or equal to 1 and less than or equal to 1 plus a constant times delta. And I'll stick to the same convention that I was using last time. Whenever I write C, it means a fixed constant depending only on the dimension, n and k. So it's got to be a fixed constant. And it's the same delta here. And also integral. And in fact, that was valid for xi in b delta 2 delta standard it. You shouldn't take these intersect support of the measure. You shouldn't take these constants too seriously. You could put any constant there. It's just to give you a definite number. Any constant bigger than 1 would be fine. And this is for every xi. You get this, and also for a good range of sigma, less than or yes. Yeah, no, it's the same delta. They're all the same delta, yeah. Yeah, that's what, see, we're using this, the fact that this was bigger than or equal to 1, we played around with the monotonicity and showed that we could vary the center point, playing with the monotonicity formula, and we got this with the same delta. Yeah, that's actually a nice fact. And then this is sigma less than or equal to 1 minus less than 1 minus 2 delta times rho. So, well, yeah, so we got those sort of inequalities. And then we had two main preliminary lemmas last time. From last time was so these are the main results so far. The first one was the affine approximation. Oh, by the way, it's very useful to note that since theta is bigger than or equal to 1, mu almost everywhere. Remember we talked about this. That implies that you can take a canonical representative for this varifold. Remember, the varifold, you can take any m that agrees with, any other m that agrees with this one almost everywhere, and any other theta that agrees with that almost everywhere. It's the same varifold then. But you can take a canonical representative, you can take, without loss of generality, you can take m equals the support of mu, which is very convenient because that means m is a nice closed set and theta is bigger than or equal to 1 everywhere. And you can also take theta to be the exact density of mu. So theta at a point x is the limit as rho goes down to 0 of mu d rho x over omega n rho to the n, the usual thing. So that's everywhere, and that's an upper semi-continuous function, remember? So that's a nice fact, that as soon as you make this assumption that the density is bigger than or equal to 1, you can actually take this canonical representative and you can actually take m to be just the support of the measure. And you can take theta to be the actual exact density function, which is very nice, because that's an upper semi-continuous function. Anyway, getting back to this, so the affine approximation lemma says that if you take any sigma less than or equal to 2 rho, 2 delta, and I think in this we took rho equals 1. Notice there's never any problem in just normalizing so that rho is equal to 1. That's just a matter of changing scale. So you may as well assume rho is equal to 1 if it's convenient to do that. So we took rho equals 1. And then any sigma less than 2 delta, and for every xi in the ball of radius 2 delta centered at 0 intersect support mu, we showed that there exists an n-dimensional subspace depending on the point and the scale. So this depends on both sigma and the point. But it still exists, and it's a subspace, n-dimensional subspace of Rn plus k, such that the sup over b sigma xi intersect the support of mu. So you look at all points in b sigma xi, and you look at the distance of the point x in the support, in this ball, to this affine space that you get by taking the center point xi. So we're talking about ball centered at xi, so it's natural to take the affine space, xi plus t. And the claim is that you can make that less than or equal to constant, again constant depending only on n and k, times delta to the 1 over 2n plus 2 times sigma. That's a very nice fact. It means that here's the picture of that. Here's the ball of radius sigma, here's the point xi. The support's here somewhere, but the support can't go all over the place. It has to be very close to an affine space passing through xi. This is xi plus t. And this height here is delta to the 1 over n plus 1. So that's a nice fact. So that was the first thing, and then we had the Lipschitz approximation theorem. In fact, this was the main ingredient in proving the Lipschitz approximation theorem. And again, same sort of thing. If b sigma, if xi is in the support of mu intersect b, again, rho equals 1, b sigma, so sigma is less than delta, bigger than 0, less than or equal to delta and bigger than 0. Then, and you take a point psi in the support of mu intersect b sigma, here. So, let's get this straight. Take any ball, xi in the support of mu intersect b delta 0. I think actually again, don't take these constants too seriously, but you can enlarge that. You can take 2 delta as a convenient number to take. And it's in the support, and that implies that there exists, and of course you've got to take delta small enough. And L given, L less than or equal to 1, given constant, given, and you have to take delta small enough, so delta should be less than a certain constant beta L to the 2n plus 2. And the claim is that there exists here beta is going to be a number just depending on n and k. So the claim is that there's a number beta such that if you make this hold, and of course we're still assuming these hypotheses, so star holds, then there exists a Lipschitz function whose graph approximates support mu in the ball centered at sigma. So there exists a Lipschitz function, f going from the ball of radius. This is a ball down in Rn because we're going to be talking about the graph approximating the support. So this is a ball down in Rn, and Bn sigma centered at 0. So this is centered at. Right. Let me. I don't want to get into this varying the center point. So let's just take let's just work at the origin. So no, in fact, I don't want to do that. Let's see. Let me stick with the same notation, otherwise I'll make a big mess of this. Okay, so there's a ball, and so this is Bn psi prime. So, let me say this again. So this is the Lipschitz approximation theorem. Namely, take point xi in the support, intersect B2 delta 0, one of the points in this ball not too far from the origin, and we're assuming star holds with this, with constant like that, where beta's, the claim is that you can choose a constant beta just depending on n and k, so that if this is true, and if you take a point xi in the support, and you take, now then you've got T0 equals, let's let T0 be this affine approximation at the radius sigma less than rho. So we're taking some sigma less than or equal to delta. So take that to be the affine approximation that appears up here. So that's our direction. And without loss of generality, let's take that to be actually Rn cross 0. Which of course you can do just by making an orthogonal transformation. So let's agree that we've already made that orthogonal transformation. And then there's a Lipschitz map on the downstairs ball. So here xi prime is the projection, is the first n coordinates of xi. So xi1 up to xi(n). So it's just the point downstairs, the first n coordinates. And that maps into Rk. And the claim is that, as I said, you can now approximate support by the graph of this function. So such that the measure of the support of mu intersect the ball of radius sigma centered at xi plus the n-dimensional Hausdorff measure of the graph. Oh, sorry. I'm talking about how well the graph of f approximates. So I subtract off the graph of f, and then I add in the measure of the graph of f minus the support. This is graph of f intersect the ball upstairs. So again, everything gets intersected with this ball upstairs. Minus support of mu. That should be now, I've got to normalize, so I'm taking balls of radius sigma, so I've got, if I want to make a sensible statement, I've got to divide everything by sigma to the by sigma to the n. And the claim is that we can make that less than or equal to a constant times delta to the 1 over n plus 1. We can make that small. So the picture of that is simply this, that here's the ball of radius sigma, here's our support. The claim is that, so this is the, so we're assuming that we've rotated so that our T0, that our approximating affine space is actually in the direction Rn cross 0. So this is xi T0 plus xi, that's the affine space. And we're claiming that we can find a Lipschitz graph that's defined downstairs. So it's defined on this domain in such a way that the graph chews up most of the support. And furthermore, the Lipschitz constant is less than or equal to this pre-assigned number L. So the Lipschitz constant here, so the slope of this picture that I've drawn, the slope of the graph, that's the yellow thing, so this is the graph of F. The slope of this thing is less than or equal to this pre-assigned number L. And the difference, see, here's a bit of the support that's different than the graph. Well, the total measure of that yellow bit that doesn't match and the white bit that doesn't match, this has the total measure of those is still small. That's the upshot of this. So you can approximate the support by a Lipschitz graph in the measure sense. The amount of measure that you miss out and the amount of measure of the graph that doesn't match with the support. Both of those things have small measure. So that's what we proved last time. So now I want to today explain the main step in the proof of the Allard theorem. So that's involves harmonic approximation. So the main step in the Allard theorem, in the Allard proof, is harmonic approximation, and I want to talk about that. Okay, so that goes as follows. There's a preliminary lemma, the harmonic approximation lemma, actually. This is just an abstract lemma that has nothing intrinsically to do with anything we're talking about here. It's just an abstract lemma about harmonic approximation. So, but it's a very useful lemma. So, suppose that you've got a function f. F is in L2 of the unit ball. So here B is the open unit ball, centered at the origin in Rn. So this is all happening in Rn, this lemma. And suppose also that the gradient of f is also an L2 function. So this is the so-called, that means f is in the so-called Sobolev space, W12. Both its gradient and the function itself are in L2. And suppose that, then for every epsilon bigger than 0, maybe I should say the quantifier first. That might make the statement a bit better. So for every epsilon bigger than 0, there exists a delta bigger than 0, such that if f and gradient f are L2 functions on the unit ball with the following, namely that the integral of gradient f squared, the L2 norm squared, is less than or equal to 1. So put a fixed bound on the L2 norm of the gradient. And the following, namely rather curious inequality that I'll explain in just a second, that if you know that the absolute value of the integral that you get when you take gradient of f dotted with gradient of a C1 function with compact support. This is integrated with respect to the Lebesgue measure over the ball. If that's small, if that's less than delta times the sup of this gradient, and if that's true for every zeta in C1 with compact support on the open ball, if that's true, then there exists a harmonic function u on the ball B, that's the open unit ball, with integral of gradient u squared similarly to f less than or equal to 1, so it satisfies the same bound as f, and it approximates f in the L2 sense. In other words, integral of b of f minus u squared dx is less than or equal to epsilon. So it really is a harmonic approximation lemma. It's saying that if you can make this integral small, at least modulo the natural factor, sup of grad zeta, and if you can do that for every zeta in C1 with compact support, then indeed you can approximate f in the L2 sense by a harmonic function. Now I should explain where this comes from, in case you haven't seen this kind of business before. So remember, Laplacian u equals 0 is the same as the sum I equals 1 up to n of this pure second derivative, di with u equals 0. And if you multiply both sides of this identity by zeta, which still gives you 0 on the right side, and you integrate by parts, then you get exactly that this integral with grad u instead of grad f is identically 0. So that's the thing. So this lemma is saying that if you've got a function f that's in some very weak sense close to being harmonic, if it were harmonic, this would be 0. But instead of that, we at least want it to be small. Then indeed, f is very well approximated in the L2 norm by a harmonic function. Very useful lemma. So let's give the proof of this. Okay. So the proof by contradiction. Suppose not. Now let's see, what does that mean that this fails? Well, if it fails, it means that there's you can find an f such that it satisfies these hypotheses for arbitrarily small delta, but it fails this for some fixed epsilon. So there's some fixed epsilon that makes this fail for every, no matter how small a delta you take. So suppose not, then there exists epsilon, positive, such that the statement there, that statement fails with epsilon equals 1 over, with delta equals 1 over k, where k equals 1, 2, etc. In other words, that is for every k, there exists an fk with the hypotheses being satisfied, so integral grad fk squared over the ball less than or equal to 1, and the absolute value of the integral grad fk dotted with grad theta over the ball. These are, of course, all these integrals are just integrals with respect to the Lebesgue measure, less than or equal to 1 over k times sup grad zeta for every zeta in C1 with compact support in the open ball. Okay, that would be what it means to fail. there's some such, and indeed it does fail. So what does it mean to fail? It means that this is always bigger than or equal to epsilon for every harmonic function satisfying this. So, and integral u minus fk squared, integral over the ball, bigger than or equal to epsilon, or actually strictly bigger than epsilon, for every harmonic function u with integral grad u squared over the ball less than or equal to 1. So that's what it means to fail. You can find a sequence like that. And now there's a famous theorem of Relic that says if you take a sequence of functions such that both the functions are in L2 and also the gradients are in L2 and they're bounded like this, then you can always find a convergent subsequence which converges strongly in L2 and even the gradient converges weakly in L2. So Relic's theorem implies that there exists a subsequence fkj which converges to f strongly in L2, converging to some limiting function f in L2, and the gradient of fkj converges weakly in L2, this is weak convergence in L2, to the gradient of it. And this f is also, this f that you get in the limit also has gradient in L2. That's part of the Relic theorem. Yeah. Oh yeah, sorry, I forgot. I didn't want to say that, but I've just, as Bob points out, I'm giving you a false theorem here. So this is not quite true. There's another hypothesis in the Relic theorem. You have to have bound on the L2 norm as well. So we've got to subtract off a constant. Otherwise, the f could just run away to infinity. In fact, there's an obvious counterexample to what I've just said. Just let fk be a constant going away to infinity, and then there's no limiting function. So I should have said there's a subsequence fkj and constants, lambda kj, such that fkj minus lambda kj tends to f. So you've got to subtract off a constant. Fortunately, that won't upset our proof. So that's the Relic theorem. Now, so we've got this limiting f, which is the limit of this translated fkj minus f. Now, on the other hand, remember we've got this this hypothesis which we can apply to the subsequence. So that's integral over b grad fkj dotted with grad zeta dx absolute is less than or equal to 1 over k j times sup grad zeta for every zeta which is C1 with compact support in the open ball. Well, but you see, this is a fixed L2 function here. In fact, it's a fixed C infinity function with compact support. So that's a fixed function. So by the weak convergence, this is the weak convergence of the gradient, weak convergence. This converges to the limiting gradient, grad f dotted with grad zeta, and that must be 0 because this side's tending to 0. So this implies that by using weak convergence, that's 0. But as I just said, that's the famous theorem of Weil. Remember I said over here that if you've got a harmonic function, then it satisfies this weak identity. But it's also a famous theorem of Weil that if you've got a function whose gradient is in L2 only, and if it satisfies this weak identity, then it's a smooth harmonic function automatically. So this means that f is harmonic on the ball B. And of course, naturally, you've got semi-continuity of the gradient, so of the norm of the gradient. So gradient of f squared, of course, is less than or equal to the limit of the gradient of f kj squared. You can easily check that using the weak convergence again. So that's just a general Hilbert space fact once you've got weak convergence. So that's less than or equal to that, and that's less than or equal to 1. But on the other hand, so gradient of f squared integral less than or equal to 1, and f is harmonic. But on the other hand, f kj, u minus f, yes. Right. What did I do wrong here? No, that's right. This is u, right. So, right. Let's see. No, we've done it correctly. Okay, so u minus f, yes, that's right. So good. So let's put f in here. So we know that we've got L2 convergence. So f minus f kj squared, of course, tends to 0. That's the Relic theorem. Strong convergence in L2. Not quite. So that squared dx tends to 0. But f is a harmonic function with gradient of f squared less than or equal to 1, and so is f minus lambda kj, same thing. It's a harmonic function with gradients. Of course, the gradient of f is the same as the gradient of f minus a constant. So that's the same. So that's a contradiction. So that's the harmonic approximation theorem. Very simple result and very easy consequence of the Relic theorem. But nevertheless extremely important. So we're going to make use of this result. Which constants? Yeah, well, I don't know about that, actually. Yeah, that's an interesting question. Do you really think there's a direct argument? You'd probably have to work a bit, I imagine. You don't like the fact you don't know the constant, huh? Actually, I thought about that, but I couldn't see any obvious direct method to prove that. So yeah, this is, as you say, is an indirect proof. So you can't actually say what the constant delta is here. You just say it exists. So I'm not sure about that. Which Bob can do. Right, okay. So that's good. So we've got this harmonic approximation lemma at our disposal now. So we're going to make use of that in proving in the main step of the Allard proof. All right. Okay, so now let me state the main ingredient in the Allard proof. Before I do that, though, I want to make a couple more remarks on harmonic functions, because we're going to use some properties of harmonic functions. So we're going to use this harmonic approximation lemma to get a harmonic approximation. In fact, I should make it clear how we're going to use this. We're going to use the harmonic approximation lemma on this Lipschitz approximation. So the notation is well chosen here. This f is going to be the same as that f in our application. So we're going to apply the harmonic approximation lemma to this Lipschitz approximation. Of course, the main difficulty then, in order to really do that, is that you've got to check that this Lipschitz approximation does satisfy these hypotheses. So that's going to be the main sort of part of the main argument to do that. But that's the idea. So that's one point, that we're going to approximate our Lipschitz approximation by a harmonic approximation. So it's sort of a two-step approximation. You first approximate by a Lipschitz function, then you approximate the Lipschitz function by a harmonic function. And therefore the harmonic function is approximating the original support of the varifold. But obviously we want to really leverage the fact that we do have a harmonic approximation, and we do that by using properties of harmonic functions. And one of the main properties of harmonic functions is that you can control the higher derivatives of a harmonic function in terms of the lower order derivatives. So we're going to make use of that fact, so I better record those inequalities here. So recall that U harmonic on a ball of radius sigma, this is all in Rn. Let's agree for the moment we'll take all balls centered at the origin, so I don't have to keep writing that. And then you get that there's a basic estimate. If you look at the order Q derivatives, dQu, high order derivatives, and you take the sup of that over a ball of radius sigma over 2, that's less than or equal to a constant depending only on n and q, times the L2 norm of U. Over the full ball of radius sigma. Of course, in this business, as in all of the results of this kind, you don't expect miracles, of course. You've got to give something up here, and what you give up here is you've got to shrink the ball a bit before you get an estimate like this. And there's one other catch here, that things have to scale correctly. And this is only depending on n and q, not depending on sigma. So the correct scaling is to put a factor sigma to the q in front of this, and then that would be scaling like u on this side. So then we have to, this is the L2 norm, which is you're integrating over the ball of radius sigma, which has got measure like sigma to the nth, but we're taking square root, so that's got measure sigma to the n over 2. So we've got to fix that up, sigma to the minus n over 2. And then that's the correct scaling. So that's the basic estimate for harmonic functions. And we're going to apply this to the gradient. So notice if U is harmonic, then trivially its gradient is also harmonic, so you should be able to apply this to the gradient function. So you also get, apply the previous to the gradient of U instead of U, and then you'll get sup d sigma over 2 dq of U is less than or equal to, again, a constant, maybe a different constant, times the L2 norm of the gradient over the full ball. So that's just the same inequality, except it's scaling a bit different, because now we're only taking n minus 1 derivatives of the gradient. Is to get the qth derivative of U, you only take n minus 1 derivatives of the gradient. So there's an extra factor of sigma this time on this side. So that's the correct scaling this time. And then these imply that you get nice affine approximations. So let's talk about affine approximations of harmonic functions. Minus U at 0 minus x dot grad U at 0. Notice we could bracket those together. Notice that would be the affine approximation. Now remember, there's a second order Taylor identity that H0 H1 equals H0, this is for any C2 function from 0, 1 into R. H0 equals H1 plus H primed at 0 plus the integral, this is the integral form of the remainder in the second order Taylor expansion. 1 minus T times H double prime of T, dt. That's, you can check this just by integrating by parts. And we're going to apply this to this function ux in the usual way. We define h of t to be equal to u of tx. Then let's see, h of 0 in that case, in this identity, will just be u at 0. And h primed at 0, which is the term that appears here, that would be, by the chain rule, that's just x dotted with the gradient at 0. And h double prime, well, that's just the second derivatives. So then you see what we get. We get that, yeah, well, I better write it. So this term, if we're taking ut of x for ht, this term becomes integral from 0 to 1, 1 minus t. And it's a double sum, where by the chain rule, we're applying the chain rule twice, so we get second derivatives, xi, xj, di, dju, at tx, integrated with respect to t. So we have that. Now notice this is quadratic in x. So, and this is the Hessian. So we get that, just using that trivial calculus identity, we get that ux minus this affine approximation is less than or equal to the sum of squares of this is just the length of the second derivatives. So it's sup less than or equal to sup. If we're working in the ball of radius sigma, it's less than or equal to sup over b sigma d2u, sup of that, times x squared, mod x squared. So we get that inequality, and mod x squared is less than sigma squared. So, but it's better to work in a slightly different ball here. So let's say the sup over a ball of radius eta times sigma. So small factor eta. What is that? Well, here we'll get mod x squared with mod x less than or equal to eta sigma. So that would be eta squared sigma squared. And this would be sup over the ball of radius eta sigma. And the sup over the second derivatives over the ball of radius eta sigma, well, that even the sup over the ball of radius sigma over 2, eta is a lot less than a half here. So take eta a lot less than a half. Let's say take eta way less than a half. So you can apply this. So this sup is certainly less, we can apply this. So this is less than or equal to eta squared sigma squared times sup. It's certainly less than sup over the ball of radius sigma over 2 then. If eta is a lot less than sigma, we're taking sup over a bigger ball, and then you can use this estimate again. So it's a power of sigma times the L2 norm of grad u over the ball of radius sigma. So that's nice. It says that this affine function gives you a very good approximation to the actual harmonic function on a smaller ball, eta sigma, and you pick up this extra factor eta sigma. Let me check that I got the scaling right, which I didn't, right? This is dimensionless, so we're thinking of u as being, well, maybe a length. So, but this side's a different scale, so this should be 2 minus n over 2. I missed out these scales. So sigma to the 2 minus n over 2, and that's the correct scale now. So, good. So that's, so you pick up this factor of eta squared, and that's going to be crucial in the argument that we give for the main step in the Allard proof. Okay, so that's as much as we need about harmonic functions. So this is a harmonic approximation lemma. and there's the general facts about harmonic functions, and in particular this affine approximation property of harmonic functions. Very, very nice property that enables you to approximate a harmonic function by the affine part of it. Just the first two terms in the Taylor series expansion. Okay, so now let me state the, before we take a break, let me state the main here. So this is the main step in the proof. This is where you use the harmonic approximation, this step in the proof. So it's called the tilde-excess decay lemma. So you assume star, same setting as before, and then the following is true, namely that for delta less than or equal to delta 0, where delta 0 just depends on n and k, so for some delta 0 just depending on n and k positive, such that if you have star with delta less than or equal to delta 0, and a sigma is less than or equal to delta, maybe I don't need, yeah, that's right. And also sigma less than or equal to delta, and xi in support mu intersect b delta 0 for the radius delta. In fact, of course, as usual, you can make that 2 delta if it's convenient for you to do so. It's just a matter of adjusting the size of delta 0 to arrange that. And and one other thing, and T equals any n-dimensional subspace of Rn plus k. Then the tilde excess there exists eta just depending on n and k. This is crucial, of course. The constants that you get, this is a constant that's very small. In fact, it's in 0.116. Small constant, but it must only depend on n and k, otherwise it's useless in the application. So there exists a fixed eta, small, such that the tilde excess in the ball of radius eta times sigma. So that means you take eta sigma to the minus nth power, and you take the mean square deviation over the ball of radius eta sigma, centered at this point psi, and as usual you take the mean square deviation, this is the tilde excess, so you take the mean square deviation away from the approximate tangent space of M. And the claim is that you can find some new direction, which we call S, some new n-dimensional subspace, and this is integrated with respect to mu. This is less than or equal to, I forgot to say, alpha is given between 1/2 and 1, but excluding 1. It's one of these Holder things. You can't achieve the right-hand limit, but you can take any alpha strictly less than 1. And then these constants, again, fibbing here, this is a constant that depends on alpha. Likewise, this is a constant that depends on alpha. Now, bigger than 0. Then you can arrange that, you can pick an eta so that if you look at the tilde excess with respect to some new direction, you can arrange that that's much smaller than the tilde excess you started with. Eta to the 2 alpha times sigma to the minus n times the integral over the same, over the original ball, p sigma psi, and then again the mean square deviation, ptxm minus p t squared d mu. So that's very strong. And this is true for some subspace, for some n-dimensional subspace. for some n-dimensional subspace S. So that's so you're saying that you start off with a tilde excess relative to a given direction, t. The claim is that you can always pick a new direction so that when you shrink the ball down by this factor eta, the excess is improved by a fixed amount, e to the 2 alpha. That's a very powerful result. Notice it's a result that can be iterated too. We can now repeat starting with S and starting with that as the new radius. And then you can repeat it again, so you can iterate it indefinitely, as many times as you want. So we'll give the proof. Let's take a 10-minute break and I'll give you the proof of this. main point is that, as I tried to explain, the main point is that if you're going to apply this lemma, it somehow looks like we're a long way from being able to do that at the moment, because this f, even though it's defined downstairs, does all its stuff upstairs. Its approximation is up in Rn plus k. So it looks like we're going to have to use the first variation formula and try to massage that a little bit in order to get an inequality like this downstairs, rather than up in Rn plus k. So that's the main sort of idea. So let's see if we can do that. We can get rid of this. So let's start. Let's hide our, we don't need to worry about this yet. We're going to try to apply this, but we can ignore it for a moment. So, proof of this guy. So you start off with the first variation formula. And this is integral over b sigma xi, working in this ball. And the usual thing, we're going to take a particular choice of x. So choose x equals, well, it's got to have compact support, so we better take care of that right away by taking just an ordinary cutoff function. So zeta is C1 with compact support in the ball. For technical reasons, I'll go right down to the ball of radius sigma over 4. You shouldn't take these columns. Any number less than 1 would be okay, but it's more convenient to go right down to sigma over 4. So this is the open ball, radius sigma over 4. And so that takes care of the compact support. And then what's the direction? That's the thing. Well, you just take a constant direction, namely the standard basis vector in the direction En plus j, where j is between 1 and k. Remember, we're in Rn plus k here. So the picture to keep in mind is this. Yeah. So, and before, I guess I should have also made some initial adjustment too. We'll do the same thing that we did here. Without loss of generality, we can take T0 to be, so T0 equals the approximation in the, let's say in the ball of radius sigma, centered at this point xi. So that gives us a sup estimate, remember, by the affine approximation, so sup d sigma xi intersect support mu distance from x. This is x. Take the sup over all points in the ball, d sigma intersect support mu. Distance x to the affine space, T0. That's less than c delta to the 1 over 2n plus 2 times the constant. Oh, by the way, Joe pointed out a couple of corrections here. I forgot the constant here, right? These are constants, and I had the wrong pad here. This is 1 minus n over 2, as you can see, because this side scales the same way as this side, except that it's got a gradient instead of u, so it's got to have a power 1 to match the gradient. The minus n over 2 takes care of the measure of the ball again. Okay, so so we do that, and yeah, well, without loss of generality, we can take t equals Rn cross 0. There is a little bit of messing about there. You've got to check that, see, you may as well assume that this p here is you may as well assume that this P here, T here is close to T0. If it's not close to T0, then you can just prove this lemma first with T0, and then you trivially get the lemma with T after that. So there's no, there is something to check there, but I claim it's a triviality. So you can just assume without loss of generality that T is equal to Rn cross 0, and that T is equal to T0. As I say, there is something to check there, but that's easily fixed. If you want to look at the details, it's all in the text. So let's get back to looking at this. So I'm choosing x to be zeta compact support function times En plus j, where j is between 1 and k. So we've got to compute div. So that's, well, div of that, so div mx. Remember, div mx is just computed using this is the matrix of the orthogonal projection onto the approximate tangent space. So it's the matrix of the orthogonal projection onto the approximate tangent space. Ij equals 1 up to n plus k, EIL DL DI XL. Sum over everything. And in this case, XL is 0 unless L is equal to n plus j. So this is just the sum I equals 1 up to n plus k di x n plus j. Now di x n plus j is is just en plus j. You don't have to differentiate the constant vector times di of zeta. That's what that looks like. And I forgot the, so this is EI n plus j, like so. So that's what that guy looks like. Now notice that that's the same as the orthogonal projection. This is the matrix of the orthogonal projection. So this is the same as the orthogonal projection. Oh, did I do that right? Yeah, I did. Because notice this depends on x. This is the orthogonal projection onto the approximate tangent space at x. So this is depending on x. So this is exactly the same as PTX MEN plus j dotted with grad m zeta. It's another way to write it. And that's the same as, this is the gradient of the n plus jth coordinate function, the gradient in Rn plus k, right, of the n plus jth coordinate function. So this actually is the same as the gradient, a tangential gradient of the n plus jth coordinate function, dotted with grad m zeta. Now, I'm not sure I mentioned it before, but when we're assuming t is equal to Rn cross 0 here. So remember we computed this. It's this quantity p txm minus pt squared is actually just twice the sum j equals 1 up to k of En plus j n plus j. We computed that last time, and using a similar computation to the one just there, this is the same as grad xn plus j squared, summed from j equals 1 up to n, j equals 1 up to k. So so we've got, so that's another point here. So one point is that the tangential divergence looks like this. So let's get that fixed first. So that means that this becomes integral over b sigma psi grad m xm plus j dotted with grad m zeta d mu is equal to 0. For every zeta which is C1 with compact support in, say, in the ball of radius sigma over 4. Actually, it would be enough in ball of radius sigma, but I want it to be even a bit smaller. It's in support. And then the other thing that I mentioned was here that T dxm minus pt squared is twice the sum j equals 1 up to k of grad xn plus j squared. So the tilde excess, the original tilde excess that you start with, tilde excess is equal to sigma to the minus n integral over b sigma xi of grad xn plus j squared d mu. And do keep in mind that by our discussion of last time, remember we can bound the tilde excess in terms of the height estimate. So this is always less than or equal to the height estimate, less than a constant times delta to the 1 over n, 1 plus n, which is small. So we do have a sort of smallness estimate. So this is sort of looking promising. This is the tangential gradient on the varifold, but it's sort of looking promising because this, instead of just working with tilde excess, now we're working with the Dirichlet integral gradient or something, and that's sort of promising because that's the sort of thing we want to get downstairs, right? We want to have gradients squared downstairs. So that's good. That's at least something. And this is also something, you see? This is, this, I don't know why I put that down. This is promising too. That's 0. And notice the form of that is very analogous to this integral. So that's encouraging. It's still not been, it hasn't yet been massaged into the exactly correct form, but looks very promising. So somehow we want to write this as a downstairs integral and show that it satisfies this smallness condition. Okay, so let's see if we can do that. So we're going to use our Lipschitz approximation. So according to our Lipschitz approximation, we can find a Lipschitz approximation with this satisfying that. The graph chews up most of the support. That's great. So let f equals graph of f intersect b sigma xi. This is our Lipschitz approximation from the Lipschitz approximation lemma. And we've got to make some agreement now about how we're going to apply the Lipschitz approximation lemma. The lemma said that we could take any L less than or equal to 1. Well, let's not be picky, just take L equals 1. So we're going to apply the Lipschitz approximation lemma with Lipschitz constant 1. So in the application, you just take Lipschitz constant 1. So lip f less than or equal to 1. And remember, you've also got a height estimate. The height estimate comes from the affine approximation theorem. In the proof, part of the proof was that the sup of f over the ball, sup of f over the ball is less than or equal to constant times delta to the 1 over 2n plus 2 times sigma. So we also have that height estimate. And while we're at it, let's keep in mind that the affine approximation lemma gives a height estimate. Did I say it already? Yeah, here it is. We also have an absolute height estimate where T0 now is, we're assuming without loss of generality, is Rn cross 0. So we actually have a similar height estimate. Oh, sorry. That's wrong, isn't it? This is supposed to be in the ball of radius sigma, so naturally it has to scale correctly. That's got a factor sigma. Without the sigma, that would be the correct inequality if you were working in the unit ball. But we're working in the ball of radius sigma now. Okay, so that's so we've got the Lipschitz approximation, and we know that it chews up most of the support. So we should be able to make use of that. So let's take care of theta first of all, though. Remember, this is theta dHn over the support. So, and theta, remember, is the density function. So theta is, remember, less than or equal to 1 plus constant times delta. In fact, it's less than or equal to, 1 plus constant times delta at each point in this ball, and it's bigger than or equal to 1. And again, this constant only depends on n and k. So let's get rid of theta right off the bat. So I'm going to replace theta by 1. So this is 0 if the theta is there, but if you take it out, then it introduces an error. I'm going to take it out. And then the error is it's got this times 1 minus theta, or theta minus 1. But theta minus 1 is less than or equal to c delta, bigger than or equal to 0 and less than or equal to c times delta. And this is less than or equal to the absolute, just use Cauchy-Schwarz. So instead of being 0, if I take out the theta, I'll introduce an error that's got a factor of c delta in it, from the 1 minus theta in the correction terms. So I get c times c delta. And then I've got to take the absolute value of these. Well, this one is, so I use Cauchy-Schwarz inequality. So I get the square root of the square of this. But that's less than or equal to the excess, tilde excess. So let's agree to let the tilde excess, let's agree to call this guy E0. So the starting tilde excess is E0. Let's call that E0. So when I use Cauchy-Schwarz, I'll get, remember, this is another way of writing the tilde excess, so I'll get square root of E0 times the sup of grad zeta. That actually is looking, in a way, that's sort of encouraging too, because having sups of grad zetas doesn't upset the harmonic approximation lemma. In fact, it's exactly what you want to get. So that shouldn't worry us, that we get a sup of grad zeta there. So we have that, and now we want to use the approximation. So let's do that. So I'm going to replace this, and for convenience, I'm going to let I'm going to call, I don't want to keep writing the intersection with support, so let's just call this d mu 0. So d mu 0 means mu 0 is Hn restricted to the support with multiplicity 1. So we've gotten rid of the multiplicity, and we're just taking Hausdorff n-dimensional measure on the support now. That's a convenience. We don't have to keep worrying about theta. And now let's do the F thing. So this is, I write this, instead of writing B sigma, I write F, which is contained in B sigma. And grad M, the same thing though. Now that, and the other term, to get back to this, is d sigma xi minus f times the same stuff. mu 0. And that's less than or equal to the same stuff here. Same stuff. But you see, this term here is less, the absolute value of this term here is less than or equal to, well, that's less than or equal to 1, that's less than or equal to sup grad zeta again, and the measure of this term is less than c times delta to the 1 over n plus 1. So I can actually simply erase this extra term as long as I modify the error term on the right. So instead of just c delta square root of E0, I actually get a C delta to the 1 over n plus 1 times E0. And E0 is much better than square root of E0, so I don't even care about the delta to the 1 over n plus 1. That's just a number less than 1, so I'm going to erase that. That's not going to help us or hinder us. Just drop it. It's, because E0 is much smaller than E0, square root of E0, so that's good. So we can just throw that, don't have to carry along that factor delta to the 1 over n. So now we have this. And now it's starting to really look pretty close to the harmonic approximation. Okay, we're not downstairs yet, but we are on the graph of a Lipschitz function. That's good. It's almost as good as being downstairs. So now let's integrate. So use the area formula. And we can write it as a downstairs integral. We can write it as the integral over the thing downstairs. Let's call it f tilde. So f tilde is the projection down into Rn cross 0 of f. And then we get a... now notice that this is the same. On f, of course, this is the same as grad fn plus j, but that's not really quite correct. Call it fn plus j tilde, where fn plus j tilde is the fn plus j tilde is a function defined in the cylinder bn sigma cross rk, so it's defined everywhere, but it happens to be independent of the first, so it only depends on the first k coordinate. So this is a function, technically a function of the n plus k variables, but it's defined to be simply the same as the Lipschitz function downstairs, which only depends on the first n variables. See, so this is a well-defined function upstairs, but it's independent of the last k coordinates, right? That's a standard trick when you're working with graphs and trying to decide whether to work downstairs or upstairs. It's often very convenient to think of the function downstairs as being actually a function that's well-defined upstairs. It just happens to be independent of those vertical coordinates, the last k coordinates. So that's what we do. And you can do the same thing with zeta. You can take that to be a function just depending on the first n coordinates and extend it in this way. So we can, these are still gradients on m though, but see that is true, isn't it? Because fn plus j tilde restricted to m is indeed xn plus j. It's the j coordinate. That's the definition of graph, right? Definition of graph. So this is restricted to m. So that means that the gradient, tangential gradient upstairs is indeed the same. Equals grad m xn plus j. So you can indeed replace this by the gradient, and now it's starting to look really good because now we've got a downstairs function, which, okay, we're working with it still upstairs, but it's still a downstairs function, so that's good. So we get that, and this can be, yeah, so we have that. Now, so that's good, we've got these error terms now instead of 0. Well, the other thing is I'd like to work over, instead of just working over this part of the graph, I'd like to work over the whole of the downstairs ball. So now, can I do that? So xi prime, remember we're talking about balls centered at the point xi upstairs. Xi prime just means the projection down onto Rn again of that point. So this is the projection down onto Rn cross 0, or Rn of xi. So that makes sense. And suppose I do that, and yes. So actually, sorry, I don't want to do that yet because, in fact, I don't want to do the area formula yet either. I just want to massage this a little bit more yet. So let's look at that a bit more. So this is the same. Yeah, I don't think I want to erase that. I didn't really want to erase that either, but that's okay. So let's look at this. I want to massage this a little bit. So this is the same as, remember, this is the orthogonal projection onto the approximate tangent space of the ordinary gradient in the Euclidean space. Now remember, these functions, even though they're defined upstairs, only depend on the first n coordinate. So the full gradient, the last k slots in the full gradient is 0, right? Because they don't depend on those coordinates. Anyway, but it still makes sense either way. And this is ptx and gradient zeta tilde. That's that. And this is the same as now. This is an orthogonal projection onto an n-dimensional subspace. That's the same as the identity minus the orthogonal projection onto the normal space, right? So I can rewrite this as orthogonal projection onto the normal space, identity minus the normal space. So I can rewrite this as the identity minus the orthogonal projection onto the normal space. D f tilde n plus j. Dotted with, again, the identity minus the orthogonal projection onto the normal space of the same thing, d zeta tilde. And that's, now you work that out, you get 4 terms. And one of them is just the identity ditto, it's just df tilde dotted with d zeta tilde, that's good. That's one of, oh, fn, I forgot the exponent, the index. That's the same as df tilde n plus j dotted with d zeta tilde. And then you get 3 other terms which cancel out and just give you minus the orthogonal projection into the normal space. I'm using the fact that orthogonal projection squared equals the orthogonal projection here. You'll see that you've got to check this computation that I'm making, but it does work out. Like that. And then this, as I said, is really down, this is actually in Rn cross 0, this vector, because the last k, it's independent of the last k coordinates likewise. This is in Rn cross 0. Last k coordinates of the gradient are equal to 0. So that's that. So I can slip in a, so I've got this term, which is the one we want. And then I can slip in a ptx m perp. And then I can slip in a p, now remember this is what we're calling t0, right? So I can slip in a pt0 minus a ptxm of that same thing, grad fn plus j tilde. And I can do the same thing on this term. So it's ptxm perp. ptxm perp. And then it's p at t0 minus ptxm d zeta tilde. Yeah, that's really, I'd like another couple of inches there. Okay, so it's that. And you see what we've managed to do there is slip in a quadratic of pt0 minus ptxm. That's extremely important because that's going to be a square exactly as appears in the, this is t0 in our present notation. So that's going to be exactly that. So that means that this expression, oh, where is it here? This expression now gives us, you get that integral over f of d, now it's just d, Fn plus j tilde, dotted with d zeta tilde, d mu 0, that's just Hausdorff measure, is absolute value is less than or equal to, the error term is like the square of the norm, pt0 minus ptxm. So we get less than or equal to the tilde xs term. So ptxm minus ptx p0 squared d mu 0. And that's, of course, you've got to take the gradients, but remember f tilde has got Lipschitz constant less than or equal to 1. So this is just less than or equal to 1, that's less than or equal to 1. So we can just put a constant times 1 there. So that's great because that's what we call E0. So this is E0 again, and we mustn't forget the other error terms that we already have. That was these. Or we had another E0, and we have this delta times square root of E0. Okay, that's great. So we have that. And now I can also replace this, well, I can write this, so the area formula enables you to write this. Remember, f is a graph of a Lipschitz function with Lipschitz constant less than or equal to 1. So I can rewrite this as an integral over the downstairs. So remember, f tilde is the projection down onto Rn cross 0 of f. And these gradients don't change, they just depend on the downstairs coordinates, except that I can remove the tilde now. And instead of d mu 0, we get the Jacobian, which is the Jacobian of g, where g is the graph map. Gx equals x fx. It's the graph map that takes you from downstairs to upstairs. And the graph, the Jacobian of the graph map, this is something we computed a couple of times, is the square root of the determinant of dig dotted with djg at x, and that's just, in this case, that really looks nice. It's the square root of the determinant of these terms give you a Kronecker delta ij, and then you get a dif dotted with djf. So that's really nice, because that looks like 1 plus big O of df squared. So so I'd like to just drop this, remember we're downstairs now, we're using the area formula, so now we're integrating downstairs. I'd like to just drop the j, and I can do that at the expense of getting an error like df squared. But that's fine, because df squared is like the, over the graph, that's the same as, remember on the graph, that's the same as this, which is the tilde excess again. So that's again an acceptable error. So this tells us that integral f tilde downstairs part of f df n plus j dotted with d zeta without the Jacobian absolute value is less than or equal to, now let's add up the errors. This is like E0, constant times E0. This one's also like E on the graph of f, intersect with the, remember f here we're taking the intersection with the part of the graph in f, so that's good. That's f intersect, so that's another one of these, so we don't have to change that. And then we've got this. Okay, so that's a little bit of a struggle, but that comes out nicely. And now we're pretty well fixed. The only thing we worried about is that, remember, f is the graph of f intersect with the support of mu intersect b. Well, yeah, it's contained in the ball of radius sigma by definition. Psi. Oh no, actually it's not, because we've got it intersect, because it could be a little bit that bulges out. So we've got to take. So that was our definition of f, the part of the graph that intersects the support inside the ball, the sigma. But I'd rather just have the whole downstairs ball here. Now, what will that cost me if I replace this by the whole downstairs ball? B sigma. Well, first of all, this support is contained in B rho over 4, so there's nothing much happening out near the boundary of the ball. But what about the size of these things? Well, that's less than or equal to 1, because Lipschitz constant is less than or equal to 1. This, we can take soup. It's not going to bother us, because remember the harmonic approximation lemma allows for soup of the test function. So that would be okay. So if I do that, I get an error involving the measure of B sigma minus F. So it would be Hausdorff measure of B sigma xi minus F would be the error, times the constant. Would be times soup of grad F, grad zeta. Notice we don't have to worry about soup of grad F once again, because gradient of F is less than or equal to 1. So we get that, but that's this thing. That's less than, it's small, delta to the n plus 1. So that's less than or equal to, oh yes, I'm sorry, I forgot the, I think I stated that one wrongly. Let's see, Lipschitz approximation. Yes, sorry, this is, indeed what I've written there is true, but it's rather important that it's actually initially estimated in terms of the tilde excess. So in our setting, this is less than CE0, which in turn is less than or equal to C delta to the 1 over n plus 1. This is the first time we've used that fact actually here. So we use that, that was the estimate from the Lipschitz approximation. So we'll get, so that'll give us another E0 times soup F, soup grad zeta. I think I had a soup grad zeta from another term, didn't I? I think all of these terms had soup grad zetas in them. Of course they did, because where else would it go? It has to be there. So, but then this term is absorbed into this with a new constant there. So that's it. As long as E0, well, actually it's not quite it, because we still have to really think about exactly how we're going to apply the harmonic approximation lemma. So let's try to get that right. Well, notice it looks like we've got a square root of E0 factor to play with, and we still get a delta which we need to apply the harmonic approximation, but we can't do better than that. So instead of applying the harmonic approximation lemma to F, we should apply it to F divided by constant times square root of E0. So apply harmonic approximation to F n plus j over c times square root of E0. Now we have to be careful about that. So then let's call that F hat. F n plus j hat. So then what do we have? We have this inequality is that the absolute value b n sigma xi d f n plus j hat dotted with d zeta dh, this is dx, so it's the leg measure now, less than or equal to, now it's square root of, we've used one of the square roots, so it's square root of E0 plus delta. And that's certainly less than or equal to, we're going to assume that E0 is small. So what are we assuming about E0? Well, it's, remember one of the, that was generally, it's less than delta, less than c times delta to the 1 over 2n plus 2. We're taking a square root, so 1 over n plus 1 becomes a 1 over 2n plus 2. So we get that. The delta, this delta is smaller still, but it's the worst power. It's because of this. Okay, that looks great. That's so the harmonic approximation. I was a bit cavalier about powers of sigma, but you can always check that using scaling, right? So this has got, so of course I meant sigma to the minus n times this is less than or equal to, this is scale invariant, this is supposed to be scale invariant too, times sup, oh sorry, forgot the sup again, sup d zeta, and that's less than or equal to c delta to the 1 over n plus 1 times sup d zeta, like so. That's scaling correctly. This is dimensionless. This is already accounted for. That doesn't change the scale. It's here. And this is dimensionless because the ball has dimension that. And the E0 is always dimensionless because it's always got the factor sigma to the minus n in front. So that's the correct scaling. Okay, so that's it. So we can apply harmonic approximation. There exists a harmonic function un plus j with sigma to the minus n. This is we're scaling correctly. Remember, where the original version of the harmonic approximation was on the unit ball. So if we apply it on the ball of radius sigma, we've got to keep this factor in front. F n plus j, f hat n plus j minus u n plus j squared is less than or equal to epsilon, as long as delta is small enough, depending on epsilon. Then we have that, and also integral grad u squared less than or equal to 1. Okay, so now we just got to go back to the original scale. Here's f hat, so I've got to put these back in. So let's agree that, let's better to call this u hat, I suppose, because I want to go back to u equals the square root of E0 times that u hat n plus j, n plus j. So let's do it that way, and then that means that just about there. So that means that sigma to the minus n, integral b sigma, without the hats, that's fn plus j minus u n plus j, use harmonic, squared, less than or equal to epsilon times E0, because I've taken a square root. No, I put the square root back now. And integral grad u n plus j squared over b sigma. Actually, this is, I think I really wanted to use, we were assuming that the support of zeta was contained in b sigma over 4. There's a technical reason for that I actually did gloss over, but you'll see that you do have to shrink the ball a little bit. As I said, you shouldn't take these constants too seriously. Any constant factor less than 1 times sigma would be okay. It's just sigma over 4 is a convenient one if you want to check all the technicalities. And then this is less than or equal to a constant times E0. Again, like that. And, okay. So now we should be able to make use of these guys now. So remember what we're trying to prove, though. We're trying to show that you can take a new direction at a smaller radius and get a big improvement in the factor in the tilt excess by doing that. So we should use these facts about harmonic function. So this is going to be what gives us our S. So define S equals the graph of the linear function L, where Lx is just this linear part of that affine function. So that's how you get your S in this. That's how you get your S. And there's a little fly in the ointment that we've got to worry about this slight translation U0. But we've got control on various terms like that. So U0 u0, absolute value of u0. I'd rather that u0 was equal to 0. That would be very convenient, because then, yeah, I forgot that I'm working here. I think it's probably better at this stage of the argument if I just say, otherwise I get in a bit of a mess here, and with 5 minutes left it's not good to get into a mess. So I think it's better to just say, without loss of generality, during this whole argument we could take xi equal to 0. It wouldn't change anything. So it just simplifies the discussion a little bit in this last bit. So without loss of generality, assume xi is equal to 0. That's fine, but that doesn't mean that u0 is equal to 0, of course. Well, u0 was whatever it turned out to be. We had no control over that, so we've got to worry about that. So mod u0, well, by the L2 estimates, mod u0 is certainly less than the constant times the L2 norm to the appropriate power, sigma to the minus n over 2, times the L2 norm of u0 over the ball of radius sigma over 4. And now it's everything centered at 0 now, if we agree on this. Of course, there is no loss of generality there, because we never vary the point xi in this entire argument, right? It's a fixed center, the whole argument. So there's certainly no loss of generality in just translating, so that's the origin. So we have that, but this can be written as c times sigma to the minus n over 2 times u minus our harmonic approximation, u minus our Lipschitz approximation, so this is our Lipschitz approximation. Here u is the vector function u1 up to uk, right? And f is our Lipschitz approximation. F has also got components f1 up to fk, back into rk. So we have that plus the norm of f. And, right. And this is L2 b sigma 0, sigma over 4 when working in radius 0. And this is, remember, this is the thing that's small. This is less than a constant times E0. That's the harmonic approximation again. And then the f, let's see, f is like, remember, a sup of f, what was that? Sup of f is less than a constant times somewhere up there. Probably got erased 20 minutes ago. But it's like a constant times delta to the 1 over 2n plus 2. Like so. So at least this u0 is small. And that's a good thing, because it means that you can, yeah, so. Okay, so now I've got a couple of minutes, so let me just summarize now. So we've got our approximation argument here, and I want to look at, and we've already defined our S now. Our S is the graph of this linear part, the approximation. So now I want to work out this guy. I'll work out this guy. So eta sigma, the minus n times integral b eta sigma, and everything's centered at 0 now. P txm minus ps squared. Okay, that's right. So that's less than or equal to. Okay. Yeah. Okay. Right. I always forget how complicated this argument is. Okay. Okay. Yeah. So yeah, heights. You want to do heights, right? Yeah. So yeah, we've done the. So let's look at heights for a start. So yeah. It's better to do heights rather than initially do this. So let's look at the heights. Integral eta sigma to the minus n minus 2, integral of f minus lambda. Now lambda is the this guy. Let's call. Oh, I'm calling it L. Okay, F minus L squared. So it's the linear part of this, and oh no, sorry. It's actually the whole thing. Sorry, L is the linear part, but this is lambda, including the 0. So F minus lambda squared. Okay, now that's over B eta sigma. So instead of immediately trying to estimate the tilde excess, instead I estimate the L2 norm of the height squared. But remember, that's more or less, that's good, because the L2 norm of the height majorizes the tilde excess over the ball of half the radius. That was one of our previous inequalities. So this majorizes the thing we're actually interested in, so that's a good thing to look at to begin with. And then we carry along this factor. I'm going to use the square triangle inequality here on this. So it's 2 eta sigma to the minus n minus 2. And then it's F minus U squared. B eta sigma 0. Oops. Plus integral of U minus lambda squared. B eta sigma. Ball of radius eta sigma. And I've still got this factor 2 times eta sigma to the minus n minus 2. By the way, notice that when you're talking about height squared, you've got to, of course, scale it correctly. You've got to put the extra minus 2 in with the radius, an extra minus 2 power radius. Now this U minus lambda squared, that's great. That's our affine estimate here. Less than this, the L2 norm grad U squared. So grad U squared is less than or equal to constant. So this term, so let's see, what do we get? Okay, from this term we get, it's here somewhere, I don't know, maybe up there somewhere. It's less than this bit gives us, this is the harmonic approximation bit, this gives us epsilon times E0, this bit, this guy. And, but unfortunately that was over the ball of radius sigma, not the ball of radius eta sigma. So we have to give we have to live with the fact that we've got these eta to the minus n minus 2 power, which looks a little threatening. So yeah, we can estimate this by as we did before, but you've got to pay for that. You've got to have a power minus n minus 2 there. But this guy, no problem. This is our affine approximation. That gives us the factor eta squared times the correct power. So we get a plus eta squared. E0. So that term is a goodie. And on the other hand, as I said, this is bigger than or equal to the tilde excess, which is the integral, but it's the tilde excess with respect to that guy. So that's integral P Txm minus Ps squared. And over the ball of radius eta sigma over 2, centered at 0. And we've still, of course, got the same factor at front, eta sigma to the minus n. Remember, when you go from tilde excess to height, you lose a factor of that, and you get a constant also when you compare that to that. So you lose the minus 2 factor. You've got to shrink the ball by a factor of a half, so you get a new constant here. But again, it's a fixed constant, and this is a constant, fixed constant. And you see, that's very, very good, because this is what we want. This is, and so it goes as follows. You first choose eta, so that this is less than, say, a quarter times E0, right? And then once you've chosen it, you choose eta to depend only on n and epsilon, right? So C only depends on n, so you can make that factor less than a quarter. Oh, you can make it less than a quarter eta to the 2 minus 2 alpha. See, because you've got a little power to play with there. You've got a power 2 minus 2 alpha. That's what you can make less than a quarter. So you can make that bit less than a quarter times e to the 2 alpha. This then, once you've chosen et, you can then choose epsilon, right? And you do that to make this also less than a quarter, or yeah, a quarter would be good, and times the same thing. And then you just have to choose delta. Both those choices depend only on n and k, so then you just have to choose delta. And that's it. You then get the required, exactly the required result, except that I lied to you a little bit at one point here. I glossed over the fact that I didn't really fully explain this, how you use this. See, what we really get here is the affine space. Well, this is the distance to an affine space. But on the other hand, the ball of radius e to sigma over 2, because this is so small, you see this is a good estimate, because this is so small, you can arrange for delta small enough, depending on eta, you can arrange that the ball of radius e to sigma over 2 is actually contained in the centered at Tor, where Tor is this guy here. You can arrange that that's contained in the ball of radius sigma, eta sigma centered at Tor. So the fact that you've got this little extra term to worry about causes basically no problem at all. You just use an inclusion of balls plus the smallness of that quantity. So that's, in a nutshell, that's a little bit how it goes. And once, of course, we are really finished now, because once you've got this inequality of the tilde excess, you iterate that, you see, and it means that the tilde excess is uniformly small at all possible radii. Now think about that. That was exactly how we defined the good set of the Lipschitz function. So that means actually that the good set of the Lipschitz function is everything. So this already proves, without doing any more work at all, this already proves that actually the whole support is the graph of a Lipschitz function. And then by leveraging this a little bit more, the fact that it decays like that, you can actually prove that it's a C1 function, a C1 alpha function actually, where alpha is the same as this exponent here. So, but this really is the hard step, the tilde excess decay. Oh, sorry, I went over time today, but it's the last lecture, I can get away with that. Thank you.
Saying that he is going to talk up to chapter 6. I think that's an impossible mission, but we made it.
I'll have to confess that we made it by leaving out several topics. But anyway, thanks to everyone for listening. That was fun to give the lectures. Thank you.
Professor Liang has spent a tremendous amount of time on this. So when everyone has a class, he skipped lunch. And he...
So I prepared at least for 1 hour.
Yeah. And in fact, he's leaving tonight. So we have the class at 10 now, and the taxi is going to pick him up at 8:30. So we are really lucky to have Professor Liang Simon to give us this serious talk. And so I